Hi, I'm Dave Robinson, and welcome to another screencast where I'll be using R to answer a Riddler 538 question. In this case, it's the Riddler Classic from May 1st, 2020, Can You Flip Your Way to Freedom? Take a look at this Riddler Classic. I've just read through it. I've read through it once. I haven't tried solving it yet. It looks like, let's give you a second to read it. You're locked in a dungeon with 3 fellow prisoners, 4 prisoners in total, no means of communication. The guards have decided to give you a single chance for immediate release. Each prisoner will be given a fair coin which can be either flipped one time or returned. If they all come up heads, you'll all be set free. If any of the flip coins comes with tails or nobody chooses to flip a coin, you'll all be doomed to spend the rest of your lives in the castle's dungeon. The goal is to get all heads, and not have nobody flip a coin. So the only tool we get are random number generators. All right, so take a look at this. The choice this prisoner has is to flip it or return it. And the other thing we can note is the prisoners can't communicate, which means the situation of the 4 prisoners is perfectly symmetrical. So logically, they're going to have to apply the same technique. You can't say, well, this prisoner does this and this other prisoner does this. They're all going to have some probability of flipping the coin. If not, now we know it's not 0 because that would mean nobody flips it, and they're all the prisoners are doomed. We know it's going to be less than 1 because, or you suspect it's less than 1 because that would have only a very low chance of 1 out of 2 to the 4, 1 out of 16 of all coming up heads. So all coming up heads. So we're going to see what probability it maximizes the probability you can be set free. We're going to be doing that first with a simulation and then I think mathematically. Just one second. Turn off my noisy air conditioning. So what I'm going to do is load up, tidyverse. What I was looking for. All right. Load up library tidyverse, and I'm going to do crossing, let's see. Yes, so first thing I'm going to do is say, to take the tidy simulation approach, we're doing 1,000 trials. Now in each of these trials, there are 4 prisoners choosing to flip a coin. And we're going to have some probability of each of them flipping a coin. That probability, let's say it goes from 0.05 to 0.95 by 0.05. Heck, I'll throw in 1. We know it's not 0, but yeah, I'll throw in 1. So now we're doing all of these trials. Now, how many choose to flip a coin? This is the trick, is I don't have a separate row for each prisoner. I'm actually going to say choose to num flips. Each prisoner is going to use their random number generator to get a probability of whether they actually decide to flip the coin as opposed to returning it, and that'll be according to rbinom with a 4 out of 4 probability being the probability being this number of probability. All right. So then here we have, okay, probability is this, and then we have number of flips. Now what we care about is the number of tails. So here we can see, like, okay, well, when the probability was 0.05, there were no flips. 0.1 was 1 flip. This is just 1 trial. But what I'm going to then say is num tail. Actually, I'm going to say num tails, and that's rbinom n out of the number of flips. There's a 0.5. So every coin got flipped. Here there was 0 flips. The prisoners lost. 0 tails. 3 flips. 2 tails. We really want to be in a situation like this where one person flipped and it was not tails, one person flipped, it was not tails. We want to be in one of those situations. This is just a couple of examples, but there are 20,000 here. So the last column I'm going to add is set free, and that is a combination of 2 factors. Num flips has to be greater than 0, and num tails has to be 0. So in this case, someone was set free. In these cases, they were not. Here they were not because one person went tails. All right, and now we've done our simulation. I'm going to make it 10,000 flips. That was really fast, so I'm actually going to make this 0.01, make it 20,000. It's a tiny bit slower. Now we have, here we go, 2 million simulations. But the reason I'm doing this is to group by probability. group by the rule that they're using, and say summarize how often are they free? That's what we're trying to maximize. And here we go. We can actually plot probability by PCT free as a genome line. It's going to be a little wiggly. Here we go. That's that shape. So we're going to really want to optimize right there. I'm actually going to make this like 50,000. And let's see how it goes. So probabilities. So this is the shape. All right, PCT. Oh, oops, I did not do. Here we go. Let's see. Oh, oop. Here, do you see my mistake? There it is. All right. So this ends up being the shape. So it looks like the best probability to have is descending. I'm just doing this quickly right away. Is descending PCT free. You want to maximize the percent of time they're free. Okay, so it looks like it can't get better than about 28%, and they're aiming for 0.34. Now, now what is the exact value of this? That's something that we're really going to care about. And here I'm going to take a look at this. There's two possible conditions. There's two things that have to be true. The number of flips has to be greater than 1. And then, so the number of flips can't be equal to 0. I could also actually, it's going to be slightly easier to understand if I say number of flips can't be 0, and the number of tails has to be 0. Okay, so the way that I'm going to think about this is if you have a probability, let's say a probability of if the probability is 0.4, then the number of flips is going to be rbinom rbinom 1 for 0.4. That's going to be one single flip. Let's make it 100. So the idea is like this is how many flips as the rbinom. Now I could also have said, what if I said what is the probability it's going to be any given number from 0 to 4? I use dbinom, the probability mass function, the density of the binomial. And now I see, okay, there's a 12.9% chance that it's 0, 34% chance that it's 1, a 34% chance that it's 2, and then this chance that it's 4, and this chance that it's 3, and this chance that it's 4. Okay, that means 12% chance you lose right away. And then for each of these, there's a probability. So it's like if it's here, then what ends up being the probability that it's all heads? Well, for that, what I can say is what's the probability it would all be heads if there were 1? That would be dbinom 1, 1.5. So 1/2 chance. If there were 2, that would have been oops. I meant to say if there were 2, it would be this, and it would be. Nope. Let me see. Hold on. Oh, sorry. What I'm trying to say is what's probably it's 1 if there's 1 flip. Okay, and then what if it's 2 that there's 2 flips, and 3 that there's 3 heads given that there's 3 flips. That's each of these probabilities. So what I'm going to do then is say. 1 to 4, 1 to 4. And now we say, oh, okay, so and I'm actually going to say, oh, well, there's a 0% chance you'll win. Your ideal is for only one person to flip a coin, because then you have a 50% chance of escaping. So you're trying to like maximize, you really would love one person to flip the coin. You'd hate if 0 people flip, then you can't win. 2 people flipping is not so bad. If all 4 people flip, you're probably not getting out of there. All right, so these are the probabilities. And what I can do then is multiply, these are probabilities for each of them. So it's like I take these probabilities that I end up with, 0, 1, 2, 3, 4, and then multiply by the conditional probabilities given that I got 0, 1, 2, 3, 4. Here's my answer, probability of winning. Sum these up. And I've got the probability of winning at, yep, see, that's about 0.4, 0.28. Yeah, actually, yeah, a little below 0.3. Okay, so this ends up being the probability that, here we go. Yeah, then what I'm going to say is probability P, probability exact, I'm going to say probability exact The exact probability given P will look like this. Here it is. This is still, the coins are fair, 1 to 4, 1 to 4, multiplied by these, probability exact, and now I say mutate exact equals map dbl, map to the all the probabilities, get their exact probability exact, map dbl for that's pairs function to add a float, to turn these into floats, into doubles. And now what I do is say gm line, color equals red, as y equals exact, color equals red. We check our math. There we go. Look at that. The simulation matches almost perfectly. I'm even just gonna say LTY equals 2. Okay. So this is how we can get the exact answer. Now we know I didn't make any mistake in this. I didn't make a mistake. So this, and actually I'm going to add num prisoners is by default 4. Actually, I'll just call it n, because that was what it was called in the. I'm getting ready for the extra credit problem. So instead of 4 prisoners, there are n prisoners. What are your chances of being released? So now I'm saying, okay, 1 to n, 1 to n. Actually, I kind of like seqlen n. It's not really a big difference. Just all right. So, yep. Yeah, and then this. Can this be vectorized? It could, but it's not. I'm just thinking about how. Yeah, so this could actually be vectorized. Okay, yeah, it can be vectorized to be a little bit more efficient. Okay, I'm actually going to go ahead and do that. Am I really? No. It's yeah. Why not? No, I'm not. All right, that was a fun little journey that I went on. But the story is here. It's only taking one probability. Maybe when at the end I'll show how we'll optimize it. Okay. So yeah, so if I said 0.24 and then 0.25, I could try and maximize this. Or I can use, so here probably is, yeah, what I can then use is single dimensional optimization. So I can say, I think there's actually a shortcut for single dimensional. We'll say optimize the probability exact function on the interval 0 to 1. No, it can't be 0. Oh wait, no, wait. That's not the problem. Is not that it can't be 0. The problem is that I'm trying to find the maximum. This tries to find the minimum. Maximum equals true. Here we go. So the maximum probability is 0.34. Yeah, I don't know. Actually, I don't really understand what was going on there. So the maximum is 0.34. Let me just look at that line again. So just to check, probably exact of 0.34 is, yeah, there it is. So the max, our ideal is that it's the ideal is that it's 28.4%. Okay, I don't have a closed form solution for that because dbinom, this function includes like combinatorics. I'm not entirely sure how to maximize it. I could try, maybe I'll try offline. I'm not going to try right now to get to figure out the exact closed form solution for this. But the story then is optim, so I can say the highest chance of escape is, and that'll be is opt, I'm going to call it opt objective when the prisoners use the random number generator to have a, I'm going to use scales percent on each of these. I'm just like to say, okay, but the story is that there's a 28% when you have a percent optim. Yep. to have chance of rolling, chance of flipping the coin. All right, so that's the shape. Oh, and I'll save it as Riddler. A lot of these are coin, prisoner, coin, flip. Okay. What about now extra credit? So optimize, I actually just found found the maximum based on this function. Now what I can do is, let's see, I'm actually going to do the simulation again, but I'm going to cross it. I'm going to reduce the number, and I'm going to cross it by n equals, if there's one player, they have to always flip, so it's not very interesting. So I'm going to do like 2 to 7, and then we'll say 2 to 7, 2 to 8, I don't know. We'll see how this looks. And then change this to the number of prisoners. Is that going to work? Yeah, I think it will. And then say rbinom and tails. Okay, that will still work. Has to be 0 tails. Okay, and then what I'll say is, here we go, change this to be sim n being extra credit. And then we'll say I can still use the same probability exact function. I wrote it to be flexible, but I'll do a map to double. Map to both probability and n. What is the maximum, the probability exact? All right. Probabilities n. What was that? What did I warn? Oh, nuts. Nuts. Let's see. Oh, yeah, so one thing is, if n is a vector, well, n will, no, map double. Let's see, so what I'm trying to figure out is, oh, there it is. Could use sequence, but let's see. 0 to n, I'm just going to use 1 to n. 1 to n. See, I had hard-coded a 4. Dbinom, let's see. Yep. Didn't need to rerun that line. All right. Now here's my probabilities n. And now I'm graphing. You know, I could use, do I use simulation? Do we use both? Yeah, I'm going to use both. What I'm going to do is quickly gather. I'm going to call this simulated. Call this simulated exact. Why am I capitalizing them? Here's why. Exact, type, value. I'm going to say probability, value, color equals n, factor n. What am I trying to do? I'm trying to get a particular kind of line that I have in my mind, a kind of graph that I have in my mind, and say LTY equals type. Hey, look at that. That's kind of cool. Call it, let's see. That's cool, but actually I kind of think it's a waste. What I'm going to instead do is do a probability exact, and then add geom point AES y equals simulated. Now I don't have to capitalize them. I was only doing that for the sake of the legend. I can do simulated exact. Here we go. That looks pretty good. Now notice it's only 10,000 each, so it's a little bit messy. And actually, I really don't need every 0.01 now that I'm not using this for the optimization. I'd rather it be a little more on the dot. Call it simin. Yep, here we go. So the story here is, yeah, I was just checking our math. So this is the lines are the exact, the dots are the probability. And now what I can see is the, let's see, probability, let's add our labels. Probability of escape. Probability of rolling, of flipping the coin. This is a fun probability puzzle. I like how it all works together. probability of escape, and then color is number of prisoners. So of course you'd rather there be just 2 prisoners. Then you have a solid chance of escape. It looks like you'd set a greater than 50% chance of flipping the coin, but the optimum does go down. Okay, and you can see kind of the optimum like decrease, 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 decrease. I'm actually going to say size equals 0.1. Make those dots a little smaller. Too small. I just don't want the dots to kind of distract from dots show simulated. So I'll say title, the chance of n prisoners. Subtitle, dot points show simulations. I like increasing our number. What the heck? We'll say of 100,000 prisoners each. I'm kind of stretching it here. That's a lot of. But this basically just checks the math. Okay, so now this shows the probability of escape does go down the more prisoners there are. Not kind of by as much as I thought there was. It's astonishing that you can have this high probability, but the story is then the probability of escape goes down, the probability you would flip a coin goes down because you're really aiming for that like 1 or 2 coins getting flipped. All right, and last thing I'm gonna do is 2 last things I'm gonna do because I like this. I'm going to labels equals scale equals %, and do a theme set, theme light. All right. All right, so that would be the probability of escape. And we see it go down. What I can then do is get the optimal value for each. So remember, I did that optimize for just 1, but I could have said, I could have said table n, the number of prisoners is 2 to 20 to, I don't know, yeah, 20. And then mutate optimal is, here we go, optimize. I would have to say, one moment while I think about this. Oh, right, I'll need optimize to be a function run on each of these. So I have to say optimize is a bit hairy. Function p, and then let's see, map double for each n. Yeah, I'll actually split this out. Optimize n. Function p sap pn. See here, I'm passing it n as the second argument here. Maybe a cleaner way to do this? Not entirely sure. Oh, not map double because it's actually named lists. Now every one of these has 2 items, the maximum and the objective. And I think unnest wider and optimal. There it goes. We have maximum. It pulls us out maximum and objective. So now what I can do is say, now if I gather metric value maximum for everything except for n, what am I doing? I'm trying to visualize as n changes, what's the how's value change for each metric. Oh, and here we go. So the and mutate metric equals if else metric is maximum, then that's optimal probability to flip, and this one and the second one besides maximum is the objective is probability of escape. I just wanted to show how these probabilities work. You know, it's actually really interesting to me that as n goes to infinity. Oh, and it does make sense. You can kind of, this is really cool. I'll get to this in a second. But let me first start. Let me start two things. Let me start by making it go out a little farther, and making. All right. Color is that. I don't want anything on color. Number of prisoners. All right. What I'm trying to show here is, check this out. Now, if I told you there were 40 prisoners, you'd say, oh no, how am I going to get exactly 40 prisoners? How am I going to get 40 prisoners to all, how am I get 40 prisoners to flip the exact right number of coins? Well, it turns out you still have a solid chance of success. Like, not solid, but like, you know, certainly not zero. It looks like it's actually asymptoting. And now if I actually make this a little longer, let me try to make it go down to 16, I expect you're really going to see, yeah, it's like asymptoting. And what is that? Why is that? I think it's because you can keep making your optimal probability lower and lower. And as you do, I think what's going to happen is that distribution of how many coins need to be flipped is going to get closer and closer to a Poisson distribution. That is, it's going to look less and less like a binomial, more and more like a Poisson. And then once it's a Poisson, it doesn't really matter what the a Poisson, when you have a binomial with a very large n and a relatively small p, which is what you'd be looking at here. You're kind of aiming for one or two coins to be flipped. So what you're looking at here then is what you look at here is like if there's 60 prisoners. Well, I'm curious if there are 60 prisoners. Optimal for n. If there are 60 prisoners, what is the probability? Arrange descending n. Then, oh, it looks like you're about a little over 1 out of 4. I really wonder if that got higher. Well, I wonder if I optimized for n on 1,000. Oh yeah, looks like it's going down to a 1 out of 4 chance of escaping. Oh, that's really interesting. That it looks like that's for something so clean. Because if I said, something got into trouble. Yeah, it looks like it's really optimizing for. Yeah, see, it got into I think the probabilities there got too small at some point. Something got a little messed up. So the story is, yeah, you end up with a 1 out, as n is very large, you have a 1 out of 4 chance of escaping. And the other question that I have for that is, descend in n, what is the expected number of coins to be flipped? Expected coins flipped is going to be n times the maximum, because the maximum is the optimal probability of flipping, because that's what the maximum represents. So it looks like you're aiming for. Yeah, I'm going to actually graph that. I'm going to graph it separately just because it's actually just the inverse of optimal probability to flip. No, it's not. It's that times 10. Well, I'm still going to graph it separately, and I'm actually just curious, like, how many are you aiming for? Looks like that's actually really steady. I'm not going to graph the same thing because it's similar. When there's only 2 people, you're aiming for like a 1.33, and then you're aiming for eventually when it gets really large, you're going to aim for 1.39 coins to be flipped. So it looks like, yeah, you ideally 1, sometimes 2, hopefully not 0, in which case you would lose right away. That's the idea is like you're aiming for a low but 1 or greater number of coins to be flipped. So that makes intuitive sense. But yeah, this is the story that as the number gets really low, as n gets really large, we can probably solve this based on the Poisson distribution, which is that I bet is going to be a little bit easier doing a closed form because Poisson doesn't have that has factorial in it. Yeah, I don't know. Now that I'm done with this, I'm going to try solving it in closed form. I usually like to solve it in code first and see the answer and kind of get a real feel for the answer first. But just to review, what we saw is that the optimal probability of flipping a coin is going to be for 2 people something like for two people, you want like almost 2/3. It's not like a 2/3 chance of flipping the coin. Once the more people there are, the lower the lower your probability of flipping the coin, and you will have a lower chance of succeeding. But we also learn from a separate graph that does level off. The chance of succeeding goes down, but it levels off at 25%. And the expected number of coins that we flip, the expected value of that level asymptotes as well, about 1.385. Okay, so that was really fun. That was solving the 538 flip your way to freedom puzzle. Yeah, I had a great time. I'm going to try writing this up as a blog post. I enjoyed myself. Hope you did too. See you next time.